Hello and welcome. Today, we're taking a deep dive into the world of advanced manufacturing, specifically focusing on the formulation of a new generation of 3D printable inks. The paper we'll be exploring is Optimization in 3D Printable Silicone DIW Ink Formulations, Gelling Behavior Control, and the Use of Carbon Nanotubes. This work addresses a critical challenge in additive manufacturing, creating materials that are not only printable, but also possess the high-performance characteristics needed for real-world commercial applications. Additive manufacturing, or 3D printing, has been heralded as a revolutionary step forward, offering the potential to overcome the limitations of traditional manufacturing in both efficiency and design. One of the most versatile of these methods is direct ink writing, or DIW. At the heart of the DIW process is the ink itself. The ink dictates everything, from the flow characteristics during extrusion to the final properties of the printed object. For DIW to be viable in high-volume manufacturing, the ink must meet a demanding set of criteria. It needs to be easily extrudable, exhibit shear thinning behavior, meaning it flows when pushed through a nozzle but holds its shape afterward, and have high thixotropy, which is the ability to become a solid-like gel when at rest. These properties are essential for creating complex, self-standing structures layer by layer. However, many existing materials like commercial adhesives and sealants fall short. While they might have favorable rheology for printing, they often suffer from very long curing times and a tendency to shrink as they cure. In a fast-paced manufacturing environment, speed is critical. You need an ink that can gel and cure progressively as the object is being built, ensuring dimensional stability from the bottom layer to the top. The researchers in this study set out to solve this problem by designing and formulating a specialized two-component silicone ink. The foundation of this ink is polydimethylsiloxane, or PDMS, which is a common type of silicone. It's a two-component system, meaning two separate parts, part A and part B, are mixed together right before printing. This in-situ mixing triggers a rapid chemical reaction. The chemistry at play is an addition-cure mechanism called platinum complex-based catalytic hydrosilylation. This is a robust reaction where hydride groups, SiH, on molecules in part B, react with vinyl groups, Cc, on molecules in part A. A platinum catalyst makes this reaction happen very quickly, forming strong, stable silicone-carbon bonds. The result is a covalently cross-linked three-dimensional network, a solid elastomeric material. Crucially, this reaction generates no byproducts, which means there is no shrinkage during the cure, a major advantage over traditional condensation cure sealants that release molecules like methanol. This formulated ink is designed to gel rapidly at room temperature and then continue to cure as the object is printed, locking in the structure's shape and integrity. Having established this high-performance base ink, the authors then explore three distinct strategies to further optimize and customize its properties for a wide range of applications. These strategies form the core of their investigation.
First, they investigate how to precisely control the gel time. In a manufacturing setting, you might need a longer working time for large, complex parts, or a very short working time for rapid production. The key to this control is a reaction inhibitor. The researchers used a molecule called methylvinyl cyclic polysiloxane, or MVC. Inhibitors work by creating a microscopic barrier, essentially phase-separating the platinum catalyst from the reactive vinyl and hydride groups. This temporarily quenches the rapid reaction, establishing a predictable working life for the ink after mixing. By adjusting the amount of this inhibitor, the working time can be finely tuned.
Let's look at their results. They prepared ink formulations with three different inhibitor concentrations, 0.02, 0.03, and 0.05 weight percent, and tested the gel time at three different ambient temperatures, 20, 25, and 30 degrees Celsius. The results, plotted on a graph of gel time versus inhibitor weight percent, show a clear trend. As the inhibitor concentration increases, the gel time gets longer. For example, at 25 degrees Celsius, the gel time increases from about 25 minutes with 0.02% inhibitor to over 50 minutes with 0.05% inhibitor. Temperature also plays a critical role. At any given inhibitor concentration, a higher temperature leads to a shorter gel time. This is because heat increases catalyst activity and also speeds up the dissociation of the inhibitor from the catalyst, allowing the curing reaction to proceed. This interplay between inhibitor concentration and temperature provides a powerful toolkit for manufacturers. If a longer working time is needed, they can either use an ink with more inhibitor or simply lower the temperature of the printing bed. For instance, the data shows that at lower operating temperatures, a high inhibitor ink provides an extended working time of about 12%. Conversely, at higher temperatures, the working time is reduced by about 20% compared to theoretical expectations, due to the combined effects of increased catalyst activity and higher mobility of the reactive molecules. The authors confirmed these findings using differential scanning calorimetry, or DSC, which measures the heat flow from a reaction. They observed that inks with more inhibitor required a higher temperature to reach their peak reaction rate, or exotherm. With 0.02% inhibitor, the peak occurred at 56 degrees Celsius, while with 0.05% inhibitor, the peak shifted up to 77 degrees Celsius. This confirms that the inhibitor effectively delays the onset of the rapid cure. This level of control is crucial for printing large footprint parts, where you need to lay down the entire base layer before the ink starts to gel, ensuring perfect fusion between printed lines. The second modeling strategy focuses on the impact of crosslinkers. While the inhibitor controls the rate of the reaction, the crosslinker dictates the structure and density of the final polymer network, which in turn governs the material's mechanical properties, like hardness and stiffness. The researchers used 3 different crosslinkers, designated XL1340, XL1341, and XL1342. These molecules vary in their content of reactive hydride, SiH, groups, measured in millimoles per gram, increasing from XL1340 to XL1342. They found that a higher concentration of SiH groups makes the system more reactive. The ink with the highest hydride content, XL1342, gelled in just 19 minutes, while the ink with the lowest, XL1340, took 43 minutes. This makes sense. More reactive sites mean the network forms faster. However, an interesting and somewhat counterintuitive result emerged when they measured the hardness of the samples just 2 hours after mixing. The fastest gelling ink, XL1342, was actually the softest at this early stage. The slowest gelling ink, XL1340, was the hardest. The paper explains this by looking at mobility. In the high hydride system, the viscosity builds up so rapidly that it traps some of the reactive groups, preventing them from finding each other and reacting. This hinders the progression of the cure, leading to a lower initial hardness. The DSC analysis supports this, showing that the high hydride crosslinker initially has a lower degree of conversion, as indicated by a smaller exotherm peak area during an isothermal test. But given enough time to reach full cure and reaction equilibrium, this trend reverses. The higher hydride content ultimately creates a denser crosslink network. This leads to a material with higher short A hardness, a higher storage modulus, a measure of stiffness, and a greater damping force, which is the ability to dissipate energy from mechanical impacts. This demonstrates that by choosing the right crosslinker, engineers can tune the final mechanical performance of the printed part to meet specific demands. The authors also examined thermal stability using thermogravimetric analysis, or TGA. They found that all the cross-linked silicone elastomers were very stable, with degradation only beginning around 385 degrees Celsius. This is a significant improvement over non-cross-linked PDMS, which can start to degrade at much lower temperatures.
This brings us to the third and final modeling strategy, incorporating a functional additive to create a nanocomposite ink. The authors chose to add multi-walled carbon nanotubes, or MWCNTs, to their base formulation. CNTs are known for their exceptional mechanical, thermal, and electrical properties. However, a major challenge is getting them to disperse uniformly within a polymer matrix. They have a strong tendency to clump together, or agglomerate, which can ruin the ink's properties.
To solve this, the researchers employed a crucial surface pretreatment step. They coated the MWCNTs with a fine mist of a fluorosilane compound. This treatment serves 2 purposes. It makes the nanotube surface more compatible with the silicone matrix, improving dispersion, and the fluorine atoms can also help tune the surface and electrical properties.
After this treatment, the functionalized CNTs were incorporated into both Part A and Part B of the ink at loadings of 0.2%, 0.5%, and 1% by weight. The visual result was a darkening of the ink, and the final printed parts showed excellent fidelity, indicating successful incorporation.
The effect of the CNTs on the ink's properties was profound. Let's start with rheology. The addition of just 0.2% CNTs caused a notable reduction in viscosity. The paper suggests this is due to a filler packing effect, where the small nanoparticles improve the interaction and flow between the larger filler particles already present in the ink. This actually enhances the ink's processability. As more CNTs were added, the viscosity increased as expected due to the high surface area of the nanotubes. Beyond 1% loading, the ink became too viscous to print effectively.
Next, the thermal properties. The results were dramatic. Adding just 0.2% CNTs increased the ink's thermal conductivity by 24% and its thermal diffusivity by 25%. This is because CNTs themselves are incredibly conductive to heat. This modification transforms the silicone from a thermal insulator into a thermally conductive material, opening up applications in heat management for electronics. The impact on electrical properties was even more striking. The base silicone ink is a fantastic electrical insulator with a very high volume resistivity. Adding a mere 0.2% of conductive CNTs caused the volume resistivity to plummet by 77%. The material went from an insulator to a conductor. Consequently, the breakdown voltage, the voltage at which the material fails as an insulator, decreased by over 99%. This demonstrates the incredible versatility of the formulation. It can be tailored for applications that require high electrical insulation, or with a tiny amount of CNTs for applications that require unimpeded electrical flow, such as sensors, circuits, or components for energy storage devices.
To verify the state of the CNTs within the cured silicone, the researchers used Raman spectroscopy. The Raman spectra for the composite inks showed a strong G-band peak around 1580 reciprocal centimeters, which is characteristic of the graphitic structure of carbon nanotubes. They also observed a D-band peak, which indicates structural disorder. By analyzing the intensity ratio of the D-band to the G-band, they could assess the structural arrangement. They found that as the amount of MWCNTs decreased, the ratio increased, indicating a reduction in order.
Finally, let's look at the mechanical properties of the nanocomposite. Adding CNTs increased the short A hardness as one might expect from adding a very strong filler. The storage modulus, or stiffness, showed an interesting behavior. It initially dropped with 0.2% CNT addition, mirroring the drop in viscosity, but then increased significantly as more CNTs were added. This suggests that at higher concentrations, the CNTs begin to form a continuous percolated network throughout the polymer matrix, which dramatically reinforces the material. The damping force also nearly doubled with 1% CNT loading, indicating a much greater ability to absorb and dissipate mechanical energy.
To get a visual confirmation of the material's internal structure, the team used a scanning electron microscope, or SEM. The SEM images of the cured nanocomposite inks are quite revealing. They show a remarkably uniform dispersion of the fillers within the PDMS matrix. There are no visible air bubbles, large agglomerates, or other non-uniformities. At higher magnifications, the CNT particles can be seen distributed randomly throughout the matrix. This excellent dispersion is the key to the enhanced properties and is a direct result of the careful formulation and CNT surface treatment. The miscibility of all components and the covalent bonds formed during the hydrosylation cure create a highly compatible and stable composite structure. In conclusion, this study successfully demonstrates a highly versatile and optimizable DIW ink system. The authors have shown that the ink's processing characteristics can be finely tuned through the strategic use of a cure inhibitor, allowing for flexible manufacturing windows adaptable to different part sizes and production speeds. They've also shown that the final mechanical properties, such as hardness and damping, can be precisely engineered by selecting crosslinkers with different reactive group densities. An increased crosslink density leads to enhanced mechanical performance, paving the way for innovative designs in advanced applications. And finally, the addition of a small amount of carbon nanotubes transforms the material, significantly enhancing its thermal and electrical properties. This turns the ink into a multifunctional material, suitable for everything from thermal management in electronics to conductive pathways in sensors. The ability to nearly double the damping force with CNTs compared to achieving a similar hardness with crosslinkers alone highlights the unique advantages of a nanocomposite approach. Of course, challenges remain. Achieving uniform CNT dispersion on an industrial scale is non-trivial. The interplay between rheology, cure kinetics, and filler loading is complex and can limit print resolution for very intricate geometries. But the authors have laid out a clear roadmap. By systematically investigating the roles of the inhibitor, the crosslinker, and functional additives, they have created a flexible platform for designing high-performance 3D printable silicone inks tailored for substantial commercial value. Future work, they suggest, could involve exploring other additives or using machine learning and simulation to further enhance the optimization process. This work represents a significant step forward in making direct ink writing a truly viable technology for high-volume, application-specific manufacturing.